Hello friends, today we will discuss Redis cluster and how it maintains eventual consistency. Now uh, in last time we discussed cap theorem, and in cap theorem we discussed consistency and availability. Partition is given. So Redis is not consistent, it is eventual consistent system and it is available. So let's see how Redis maintain its availability in a distributed system. So today we will talk about the Redis cluster. So let's say we have one, leader node. Let's say in Redis cluster, you need to have 3 leader nodes, and then you can have multiple replicas associated with each leader. So let's say these are one replica associated with each leader, and then let's say we have a number of clients who are connecting. I'll just creating one client here for now. Now, so in general, how this cluster will work is whenever you bring on this cluster, right now we have 3 leader nodes. So these nodes would share among them the hash slots. They are around 163 84 uh, slots. So these slots are divided from 0 to this value divided by 3 and so on and so forth. So equally divided into three sets of slots, and each set is associated with each of these leaders 1, 2, 3. And a client is tried to whenever client try to save the data, and in this case in Redis, client is intelligent. So even before it saves the topology of the whole cluster, that means the client would know that there are 3 masters, and it will hold the IPs of those masters. Now, how come client know about these masters? So there are multiple ways you can do that. One way is to seed it. So you need to give at least one IP address uh, in the config file, or if you are using some orchestrator discovery service, then client can get that information from that orchestrator. But if with that one IP, it can be any IP of any of these 3 masters. It get, or even in nodes, replica nodes, it get the information about the whole topology. That means information of the IPs of the whole masters, leader nodes, who are the leader nodes, and who are the replicas. So it has all the mapping of all that information. Now, once the client has that information, then the client has an algorithm which, based on the string key, it it uh, uh, it decide apply the algorithm, get to know that in which group of hash slots this key falls. So let's say it falls into, so that key is saved in this master. So for all such keys, it resolve against a hash slot using a same algorithm and decide where it goes, where it will be saved, and it has the IP. So it, using that IP, it save that key in that leader node. So now let's say uh, one of these node fails. Let's say one fails. So what then happens? So clearly, if you have just sent a request to this one, and even before it got replicated to the replication node of the leader one, this fails. So clearly that information is lost. Now to avoid that, you can use wait. and you can mention how many replicas should have this information before any leader uh, send the acknowledgement that okay, I have saved your value. Let's say it said that okay, in this case only there is one leader, one replica node, but let's say there are multiple replica nodes. So this client send this a request, and with the information, okay, I want to wait, and I want to acknowledge me only when this is saved in at least one replica, this information. So in this case, if that is set, so the master would not acknowledge until it gets an acknowledgement from one of these replicas that they got the value. Now, if in this case, let's say if you are using wait, and um, this master fails without acknowledging the client, that means clients need understands that okay, now whatever I have saved, that has not been saved in this leader node. So you can write a code to handle such situation in clients. But let's say you are not using wait, because wait cause an overhead, slows you down, because there is another network hop here, and some processing, and that processing depends upon the load. If there's a lot of load, then, and remember, Redis is single threaded. Redis servers are single thread. That means only one thread will actually be doing all the work. So that is why it is recommended to create smaller nodes, and a lot of them, to utilize your cores. Uh, so let's say in the worst case scenario, you are not using the data interface. So in that case, you lost the data, and if you try to access the data again, uh, there are two things, like eventually there will be failover, and there will be new leader selected, and that leader would not have the data. So eventually you would not get the data. But let's say at the same time you try to access it, and the master is already gone. This leader node is already gone, is dead. So there is no response for this client. Now at the same time, failure mechanism is taking place in the cluster. So this whole cluster, all the nodes are using gossip protocol, to get the information about each other. So one of the information is the health information. So in this case, when the one leader one goes down, all of the nodes eventually come to know that this is not responding. So initially they will set as probable failed, and eventually after a few clings, if still it does not respond, then they mark it fail. Now, as soon as they mark it fail, one thing happens, that all the master knows that this node has failed. Now the second step is these replicas reach out to remaining masters, both of them. Who does this? The other one. They reach out and put their nomination to become the new leader. Now what happens that these nodes are equal. So how these remaining leaders decide which one should be the new leader out of these two nodes? So they decide on three parameters. First thing is, there is there, as a admin, you can set a preference out of which well, you can set a ranking from starting from 1 to 100. One is the top rank, which means top eligible, top replica eligible to become leader. If you set 0, that means it will never contest for leader. So let's say any of these nodes has lower, higher rank, that is less rank. Like let's say one is 1 and other is 2, so one would get the preference. Let's say both of them, like you have set it default and it does not change their ranking. Then other thing is, what is the amount of data they have? What is the last offset? Whichever has the highest offset would be preferred by both the leaders, both the quorum, and they will vote for uh, that replica. Let's say um, both of them has the same offset. Then what? Then then they whenever we set these nodes, a name is provided, a ID is provided to all these nodes. So whoever ID is, has uh, what do you call it? Like, let's say in a alphabetical order, it can be alphabetical, but let's say in that order, if you sort it in a ascending order, so whichever is the first item in that row, that list would get preference. So this is how it is sorted. So eventually, there's a mechanism that okay, even all the uh, you know um there's one more thing which happens before that. If whoever whoever send the request first to first to a node, leader node, that leader node would prefer to give the vote to that uh, in favor of that replica node. All thing remains same. But then if that also does not work and two nodes come at the same time, then the last thing, the ID is used to do the tiebreaker. So this is how, and once this is done, while you remember the client is still hanging, so it once it does not get request from this master, it tries to reach out to some other node, and this node would redirect this client to the new master. Okay, so now it gets the new IP, new topology. Now, if this master happens to come back, the master one happens to come back, then uh, then it will not become the new leader. It will just become a replica. This is how the replica. This is how a failover works in case of Redis cluster. Now we see two things. One is okay. It is a you need at least uh, three leaders. Uh, uh, or n divided by 2 plus 1 leaders to start with, and assuming only one fails. And the minimum size, cluster size is you must have three masters um, to start with. So with this, there is the automatic failover. You don't have to worry about this. Uh, Other thing is you will lose data. Uh, in Redis, you can save the data. You can persist the data. By default, it does not persist, but you choose to persist. If you try to persist it, then even it become even slower. That is mostly, so again, this is a choice which you have to make based on your requirement. Other than that, so we see that okay, we may lose data. Uh, uh, Now there is one more thing, which happens is that let's say you want to. Now this is a localized cluster. You have all this cluster in a single data center. But let's say you want to have a cluster in different geographies, so that even if whole data center goes down, then still you have availability. Now in this case, you have two choices that we need another. So in that case, let's say you have two geographies, and let's say you have again clusters. So if you want to deploy your, this Redis cluster across geography, you better take enterprise Redis to solve that problem, because the problem is, before we discuss that problem, let's see why you want this. So you would need this, let's say, because you want whatever you are doing, it is very important. And if one data center goes down, you can't afford to lose the availability. You want to keep your system available to your clients. That is the most important reason. Second thing is, let's say you are running something, uh, which is like lots and lots of requests is coming. and across the whole, multiple geographies, or multiple continents or multiple areas. Uh, the requests are coming in. You know that if the distance needs to, your request traveling so many hops from this continent to this continent, A continent to B continent, we'll have a lot of hops, a lot of routers, wire, everything. So it takes some time. So to reduce that, what you want to do is you want to deploy your software close to your user. So in that case also you would like to have such a configuration where the data of a user or a group of user are closer to them geographically. The problem with that is that you are splitting the data based on the geography. So the users of A geography, let's say A geography and B geography. So all the data of geography A resides in this cluster, and all the data for B resides in this cluster. Now again, the only problem this is solving is to reduce the network latency. But again, it is not providing you the geographical availability. If one data center goes down, let's say this research center goes down, the a set of users will lose availability. Uh, so how you can solve this? Like if you have a free version, then what you can do is you create the replicas in another geographies. What that means is that the replica of this is here, and a replica of this is here. So even if this goes down, you have uh, you have the data in the data center, and eventually user would, and then you have load balancers, which are geographical aware load balancers. First they will detect which geography user is coming, and then they will redirect to a particular nearest node. But if they detect, okay, this is down, then definitely they will detect to the other uh, data center. So that way this client would go there. That is one solution. But again, the problem is now you can see there is a long hop. So again, performance is reduced because there is a lot of network involved. So the original requirement that we want both the things. One is we want availability, and we want performance, like the reduced network latency. The there is you need to buy the enterprise edition of Redis. So what that will do is, let let me see if I can get it. What we will do, there is a concept of active. What that means is these two, let's say these two uh, leaders share the same hash slot. What that means is, although A is sharing here, but this would be replicated to here, and then you can switch on then there is a concept of synchronization, which means that, okay, the acknowledgement will not come from this leader until this leader has that saved the data. So that means, like, okay, this is kind of a synchronized, kind of a consistent. The latency is reduced. So, for example, uh, this will not acknowledge this will not acknowledge until this also have the same data. So that means if we tries to get data from here, it will get it. But again, it is like not consistent in the consistent way, uh, because you have the data here, but while the data is being written here or traveling, you can at the same time you are accessing, you would get different data. So they're not um, guaranteed consistent. Consistency is not guaranteed here, but it is very close to that. Uh, but again, it is available on only enterprise Redis. Uh, you can do something similar, but then with the free edition, but you have to do a lot of your own bespoke logic, which is not recommended. So I think we covered the cluster, failover, how client got how client works and how it topology, how it identify a topology basically client, uh, how multi-region cluster works. Okay, so I think we have covered the areas which I have to cover in this session. The primary idea was to see how a highly available highly available system handles failover. So I think we have covered that. Now maybe it is a time, in the next session we may cover something, where what about a CP kind of system which is highly distributed. So let's see, we'll cover that in next session. Thank you guys.